Everyone, please welcome Michal from Nethermind. He'll be giving a talk on Mova, improving Nova folding scheme. Please give a warm round of applause.
Thank you. So thanks for introduction. Yeah, let me talk about Mova and like folding without commitment to errors. So maybe let me begin with why folding and what folding is. So basically, when we talk about zero-knowledge proofs, so we are talking about proving particular relations. And this relation takes usually two inputs, one being some statement, here X, and another being witness. In zero-knowledge proofs, statement is, statement is public and witness is usually private. This is the value that we want to hide from the verifier. Right. So in folding scheme, we have our usual suspects, prover and verifier. So in this case, prover has as input two instance witness pairs, and similarly, the verifier has two instances to be verified. So what the prover wants to show is that both instances belongs to some relation R. So in folding scheme, prover and verifier interact to create some sort of joint instance witness pair, here X3, W3, with a very particular property, namely if this if relation on X3, W3 hold, then relation on X1, W1 and X2, W2 hold as well, right? So we somehow reduce two instances into one. Okay, so why do we care about folding? So we have our two relations, X1, W1, X2, W2. We fold, we come up to X3, W3. So we can reduce a task of proving two instance witness pairs into proving one instance witness pair, okay? So you can imagine that if you have like a prover that was tasked to prove like both X1 and X2, at the end of the day, the prover needs to prove something much smaller, being like X3, W3. I mean, it's not smaller than each of the X1 and X2, but it's smaller than proving like both separately. So here we need some design principle, namely the folding itself needs to be relatively cheap. Like it needs to be cheaper than like proving the instance witness. And one of the applications for proving are so-called continuations. So you can imagine that you have like a super big computation. Think about like, I don't know, like ZKVM execution. So what you can actually do is you can divide this very big relation, this computation, into much smaller chunks and fold all these smaller chunks, all these instances, into a single small chunk, and then prove this small relation instead of proving this very large relation. Another use case is like efficient incrementally verified computation of proof-carrying data. Okay, so before I go into Mova, let me talk about Nova. So this is like, I believe, first folding scheme that became very popular thanks to the work of Kutapalli, Sethi, Tsealia. In Nova, the authors defined something called committed relaxed R1CS relation, which is roughly the relation as follows. Maybe I can, yeah. So on the left-hand side, we have our instance and witness, commitment to instance and witness that is denoted as a Z with bar. In general, like throughout this talk, I will refer to committed values as values with bars. And we have some error term E with also bar. So here, you see like our well-known like R1CS relation, but with some twist. So A, B, and C are matrices that describe our computation, our circuit. Z is our witness, so like the evaluation of the circuit gates, and E is the error that comes from folding, right? And because ABC denote the computation we are doing, our circuit, these are public matrices. Importantly, we have also access to the commitment, to the witness and the error. Okay, so let's take a look at Nova from 5,000 feet. So we have two relations, two relaxed committed R1CS relations. So we have Z1 bar, E1 bar. So this is like the public part. Z1, E1 is the private part. We have Z2, E2 bar with bars, the public part, and Z2 and E2 as a private part. Okay, and this is given to the prover, of course, like the both public and private part. Verifier learns only the public part. So what prover does is it commits to a vector T that is like a commitment to so-called cross terms. This is like a big part of Nova. And verifier responds with some challenge alpha. And P and V jointly compute this folded relation Z3, E3 with bars on their own. Okay, so why they can compute this Z3 bar, E3 bar, it's because like Z3 and E3 are linear combinations of Z1, Z2, E1, E2, and T. So here this alpha Zi, alpha Z2 are values that are derived from this alpha here. Right, and they are like publicly known because the alpha that V sent is known. Okay, so how we compute the commitment to Z3 and commitment to E3, and here is where we are using the homomorphic property of the commitment scheme, and homomorphic property here means that if I have a commitment to some value A and I have commitment to a value B, then when I add these commitments, I have a commitment to value A plus B. And similarly, we can use these coefficients alpha Z1, alpha Z2, etc., and commitments to Z1, Z2, E1, T, E2 that I know to compute the commitments Z3 and E3. Okay, so let's talk about cost. So yeah, the vector T is called cross term, and committing to T is like a bottleneck of this scheme in many cases, in many like real life cases. So and this is because T is filled with random field elements, and so like each entry has like a logarithm of the size of the filled bits. And this is actually committing to such vectors is actually quite expensive. So we need like roughly like 2 to the 8 times T field operations, T like size of the vector field operations. And this is like a dominant cost. So to provide some concrete benchmarks, so we looked at Pedersen commitment over a Pallas curve, and the commitment to T. Like here we have like the size of the witness, commitment to T. It also depends, of course, on the size of the witness. And like in Nova, folding instance of size to the 16 like took roughly half of a second, and like 88% of this time was the part where we had to commit to T. Okay, so now let me talk about Mova. So Mova allows to fold instances without committing to E or to T. Okay, so first question is, why does P need to commit to T? So the only reason why P needs to commit to T is like it allows the verifier to compute the commitment to E3, and this is because, like, yeah, as we said before, there's this E3 is like LC, like here stands for linear combination. So E3 is linear combination of E1 bar, T bar, E2 bar. Okay, by what if V needs to compute E3 bar? So so actually, this E3 bar is a part of an instance in R, right? So that was our relation. But do we really need E3 bar in this relation? So maybe not. Maybe not, because, like, as we observed, the commitment to E, to this error term, is actually redundant, and this is because E3 is implicitly committed to by commitment to Z3 bar, and this holds from this equation below, right? So if we have like public values A, B, C, well, and you, sorry for confusion, you shouldn't be here because, like, we have this simplified version of relaxed R1CS instance, and we have Z3. Then like this E3 is like known, right? It's like we can solve this equation. So the question is, like, can we actually just delete E from the definition of R? And this is no, not really. Like there are some technical details why we cannot do that. And like to give like some overview of the technical details, when we commit, when we reduce R1CS instance to commit relaxed R1CS, we actually need to beat E to be 0. And in Nova, it's done by setting the commitment to E to be a commitment to 0. And this is why we need to commit to E in R. But actually, we realized that we can do some trick and replace commitment to E by an evaluation of multilinear extension of E at a random point. So what we do is that we introduce relation R prime that has some additional values V and R. And instead committing to E, we have this multilinear extension of E at some random point R, and the claim is that this multilinear extension gives value V. Okay, now we require prover to send this multilinear extension instead of sending the commitment to T. We also do some randomization of the point R and each folding step. Okay, so how Mova look like? So this is our relation. We have prover, verifier. Prover has like the pair of relations. Verifier has like, sorry, pair of instances. Verifier has also like a pair of instances. Here we assume that R1, R2 equals R, but this is like a technicality. So the first thing, like the prover sends, is this multilinear extension of T at R, and V replies with some challenge alpha, and this way we get like a new folded relation. And here the trick is that, okay, so as previously, like Z3 is just like linear combination of Z1, Z2. E3 is linear combination of E1, T, E2. And Z3 is like linear, Z3 bar is a linear combination of Z1 bar and Z2 bar. And actually, like this multilinear extension of E3 over R can be computed as a linear combination of these multilinear extensions that we already know. Okay, so regarding performance improvements, compared to Nova, we observed over 6-time improvement for instances of size like 2 to the 16. For 2 to the 20, actually, like the improvement is a bit smaller. This comes from the fact that Nova actually like performs a bit better with higher instances. So the setting we did that was like the R1CS witness contained only like small entries. ABC were identity matrices, and like Mova's verifier cost is similar to Hypernova verifier, but we have like constant number of rounds, and Hypernova has logarithmic number of rounds. Yes, so here we can see like a matrix of this performance of the scheme. So for Nova, like we see that prover like has like smaller number of like field operations, but we also need to commit to T, and that what makes Nova much less efficient. Okay, and one additional thing here is that in our work we try to answer question like, can we have like efficient R1CS folding scheme where the prover commits only to witness, and the number of rounds for verifier is constant? And we thought that we were first to answer this question like affirmatively, but actually like Ariel's Gabizon work on Protogalaxy was also like answered this question positively. And like from some perspective, that Mova is some sort of specialization of Protogalaxy scheme. Okay, thanks a lot. I'm happy to take questions if we have time. Feel free to connect using this QR code.
Let's take one question and then move on to the last talk. Any questions from anyone in the audience? Okay. Thank you so much, Michal. Great talk, and we appreciate you coming. Thank you so much.